Welcome to Lecture 18, whose subject matter is waves. Waves are among the most important phenomena in physics, and actually, for that matter, in your everyday life. You wouldn't hear without sound waves, you wouldn't see without light waves, you wouldn't get a speeding ticket without radar waves. We'll see later in the lecture how that happens. I've got some video clips here of waves, a beautiful example of an ocean wave breaking. What happens when a water drop falls into a clear patch of water and ripples spread out in all directions. Those are waves. There's a simulation of sound waves. An earthquake wave, a simulation of an earthquake wave traveling through the planet. And you see the wave of standing people going through the stadium as people rise up, and then next to them people rise up, and the wave propagates along. Waves are closely related to the oscillations we talked about in the preceding lecture, except that there, where I had my big yellow ball just bouncing up and down on its spring, in a wave, an oscillation occurs in some part of a material medium, or as we'll see later, in vacuum also, and that disturbance is propagated to nearby regions, and as a result, a propagating disturbance moves through the medium. That propagating disturbance is a wave. So let's look in a little bit at some of the details of waves, and then we'll see some of their fascinating behaviors. To begin with, a wave is a traveling disturbance that carries energy but not matter. Let me make that very clear. Waves do not carry matter. They carry energy. They may involve matter, as sound waves do, as water waves do, as earthquake waves do. They may disturb matter. The matter may temporarily move as the wave goes by, but the wave is not the matter, and the wave's motion is not the motion of matter, but of energy. Let's go over and do a couple quick demonstrations that illustrate these points. So here I have a stretched spring. Like many material structures, it will easily propagate waves, and I'm going to generate a little wave pulse on it by disturbing it from its equilibrium position. And when I let go, you'll see a pulse propagate rather rapidly down the spring. It will, in fact, reflect at the other end and come back. So here it goes. Now, that particular wave, which resulted from a disturbance at right angles to the spring's dimension, is called a transverse wave. It's transverse because the disturbance that constitutes the wave is transverse or perpendicular to the medium on which the wave is propagating, in this case, this sort of one-dimensional spring. So that's a transverse wave. Some waves are transverse, some are longitudinal. Light waves, for example, are transverse. What's a longitudinal wave? Well, a longitudinal wave happens if I make a disturbance occur in the direction of the medium. So if I squish some of this spring here and then let it go, you see that region of compressed spring propagate down the spring and back. That's a longitudinal wave. Sound waves are examples of longitudinal waves. In either case, the spring didn't go anywhere. It temporarily moved back and forth or up and down as the wave went by, but the spring itself stayed in one place. A wave is a traveling disturbance that carries energy but not matter. So we'd like to describe waves mathematically a little bit because we're doing this course mathematically. So let's go over to our big math screen and let's look at some wave math. How do we write a function that describes a moving wave? Here's an example of a sinusoidal function. Sine of x, x is position, and the red curve is plotting the sine of x. I'm going to talk about waves that are sinusoidal in shape. Waves don't have to be sinusoidal, but it turns out you can make any kind of wave out of a sequence of sinusoids. So I'll just pretend waves are all sinusoidal. It doesn't really make any difference. It doesn't lose any generalization. If I wanted to plot sine of something else, for example, suppose I plotted sine of x minus 2. What does that do? It takes the place where x was 0, and it moves that to when x equals 2, because sine of 0 is 0, sine of 0 is 0, but 0 occurs in this case when x is equal to 2. And so the effect of that is to move the whole sine wave to the right by 2 units on that axis. So this is sine of x. This is the same function, but its argument, the thing that the sine is acting on, is x minus 2. Now that gives us a hint about how we can describe a wave that's moving. Instead of just putting 2 there, we can put a function of time. In fact, we can put velocity times time, and then we will get a moving wave. So there is sine of x minus vt, where v is the velocity of the wave. And you can see what's happening. The wave is moving along. That point that was originally at 0 is moving to the right as time t advances. And this number vt starts out at 0 and gets bigger and bigger and bigger, passing through 2, 4, 6, 8, and so on. So A wave is described by a function of position and time, and the way position and time enter that function is in the form of position minus velocity times time. That's how we make a wave move. So here's our moving wave, sine of x minus vt. Let's take a look at what this wave looks like from 2 points of view. At a fixed time, if I take a snapshot of that wave at a fixed time, I see a sinusoidal curve that gives the displacement, I'll call it y, as a function of position x, from some amplitude a down to the opposite of that amplitude minus a. Between the crests of the wave is a number which is called the wavelength. It's a distance. On the other hand, if I take a picture of the wave at a fixed position in space and let time vary, so I sit at a fixed position and watch the wave vary as it goes by, I again see an oscillation with amplitude from A to minus A. But now I've got time on this axis, and there is a certain time it takes the wave to repeat itself, and that's called the period of the wave. So we have the wavelength, given the Greek symbol lambda, and the period, given the symbol capital T. The wavelength is the distance between wave crests. The wave period, T, is the time between wave crests. And now here's the important point we're going to need. The wave moves one wavelength lambda in one period t. If you sit at a fixed position, the time it takes to go from that crest till the next one passes you will be this period t. In that time, a distance lambda of the wave has gone by, and that means that the wave speed is lambda over t. So the wave speed is simply the wavelength divided by the period. The wave frequency is 1 over the period, the same as it is for oscillatory motion. You give me the time it takes for one wave cycle, and I can invert that to get the number of cycles per second. Frequency is 1 over t. So another way of writing this is that the speed of the wave is lambda times f, lambda over t, or lambda times f. So that's what a wave looks like, and that's how we describe it mathematically. Now, waves have some unusual behaviors. And one of the most important behaviors waves have is that they can interfere. Unlike matter, two waves can be in the same place at the same time. When I was running waves back and forth on that spring, you may have noticed that the reflection was coming back while I launched a new wave, and those two wave pulses just passed right through each other, and then they were gone on their separate ways. While they're on top of each other, the disturbance of that spring was the composite disturbance of the two different waves that were acting at that point, and then they went on their way as if they had never met each other. That's the phenomenon of wave interference, the fact that two waves can be in the same place at the same time, and when they are, their amplitudes simply add, or maybe they subtract if one wave is going down and one wave is going up. And there are a number of important phenomena that result from wave interference. Wave interference is going to prove vital in our study of physics. For example, in quantum mechanics, we'll use wave interference to understand some very unusual phenomena. We can use interference to make some very critical measurements. The theory of relativity was established in part as a result of an experiment that involved interference. Interference of waves is a really crucial way of measuring many, many kinds of things. So let me look just at a couple of wave phenomena. One phenomenon which occurs with sound waves, although it does occur with other waves too, but we think of it in terms of sound waves, is the phenomenon called beats. And you've heard beats if you've ever been sitting in a two-engine airplane, and the engines aren't quite going at the same speed. And the airplane is kind of droning along and keeps getting louder and softer. Why is that going on? Well, I've got a picture here that suggests two waves of slightly different frequencies. So they're not exactly in synchronism. So what happens as the waves move along is sometimes two crests coincide and the wave gets bigger, and sometimes two troughs coincide and the waves cancel out. And that happens very gradually if the frequencies are very close. And so even though the waves themselves may have relatively high frequencies, the frequencies of these beats you hear are much, much lower. So that the airplane's engines may be making noise at a fairly high frequency, but that drone may be every second or two. And the pilots, if they listen to that, can carefully adjust their throttles and get the engines going at just the right speed. That's the phenomenon of beats. It occurs because of the interference of waves of nearly equal frequency, and it provides an audible indication of whether frequencies are synchronized. And it also enables some very, very precise measurement techniques by detecting that very small difference in frequencies. I'm not going to spend the time to prove it. Give me 10 minutes at the big screen, and I could show you exactly how that beat phenomenon comes about, and I could show you that, in fact, the beat frequency you hear, the frequency of the is exactly half the difference frequency of the two waves. But don't take my word for it. Let's do an experiment in which we'll actually hear beats occurring. So here we are with some equipment which will allow us to actually hear the phenomenon of beats, interference of waves from two different sources, in this case sources of sound. So what do I have here? Most importantly, I've got a couple of loudspeakers that are going to produce sound waves at almost but not quite the same frequencies, and they're being picked up by this microphone so you can hear the result. The sound waves are going to be made by the loudspeakers, which are fed electrical signals from these two signal generators, and they're both set to 1,000 hertz, 1,000 cycles per second sound. So in every second, these sound waves are going to go up and down, oscillate 1,000 times a second, and we'll hear that as a particular tone. I'm also looking at the outputs of those signals on an oscilloscope, which is a device that looks at electrical signals as functions of time, and we have the oscilloscope hooked up through a cable to the big screen monitor, so you'll be able to see what the oscilloscope is displaying. So let me get started. I'm going to turn on the 2,000 hertz tones, and you can hear them, and they sound pretty steady because they're both at essentially 1,000 hertz. I'm going to get the oscilloscope set so we'll look at the two of them, and there they are, a yellow and a green corresponding to the outputs of those two signal generators that are being fed into the loudspeakers. So there they are, yellow and green, and the fact that we see them both kind of locked in place on this screen tells me that they're at very, very nearly the same frequency. Not perfectly, the yellow one's drifting a little bit because these two signal generators don't know about each other, but they're pretty good ones, and they're both set to 1,000 hertz. Now I'm going to change the frequency of one of them by a little bit, by 1 hertz at a time, 1 cycle per second at a time. So here I go. I'm going to turn it up. There it is, 1,001. And you see the yellow curve beginning to drift because it's no longer at the same exact frequency as the lower curve, and you begin to hear the beats. Remember, the beat frequency is half the difference. Here the difference frequency is 1 hertz, so the beat frequency is half a hertz, or 1 cycle every 2 seconds. Let me turn up the difference frequency. Now you hear the beats more rapidly. Wow, 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 wow. That's the phenomenon of beats. Now, let me do something else. Let me turn the beat frequency up a little bit more. Let me turn it up so one signal generator is going at 1,030 hertz and the other one's still going at 1,000. So the beat frequency will get to be about 15 hertz. And that's slow enough that you can still just barely get a sense that there are individual beats there. So you're hearing a kind of 30 hertz vibration superimposed on the 1,000 hertz signals. And now let me change the oscilloscope display so that instead of looking at those two signals, it looks at their sum. I'm going to get rid of the two. And I'm going to change the time scale so it'll be more appropriate to the slower time scale of the beat frequencies. And let's look at what we have. Here we have the very rapid oscillations that are occurring about 1,000 times a second, approximately 1,030 times a second for one of them and 1,000 times for the other. And every so often, the two of them get in phase, so they peak at the same instant, and that's when we get this very big signal, and that's when the sound is loud. And then, as time goes by, they gradually drift out of phase until we reach a point where one of them is at its peak while the other is at its trough, and there they completely cancel out, and these are these low spots you see in between. So that's the phenomenon of beats. It's representative of wave interference, and it provides, as I mentioned, techniques for some very, very sensitive measurements. So here we go. Two-source interference. I'm going to imagine I have two sources of waves, like making rocks dropping in a pond, for example, and making ripples. They're going to spread out in all directions. These could be sound sources, light sources, water wave sources, whatever. The idea is the same. Two sources, they're pulsing together at the same frequency, and they send out wave fronts. These are the crests of the waves illustrated here, and they spread out further and further and further. Now, what I'd like you to focus on are regions like right here where two wave crests meet. Another place where two wave crests meet. In between, two wave troughs meet, and so we have a really deep-going wave. On the other hand, there are places like right here where a wave crest is meeting a trough, and those are places where the wave amplitude is going to be very small. So if we think about it, what we're going to get here is a pattern of wave interference in which there are lines of strong waves. If these were light waves, somebody looking in from here would see bright regions, bright regions, bright regions, and in between dark regions. Somebody listening to sound coming from two loudspeakers fed from the same source, as they walked transversely like this to the two sources, would hear loud, soft, loud, soft, loud, soft, because of this wave interference. Two-source interference is going to be vitally important in much of what we do in this course, especially when we get to quantum physics, because it's going to tell us some things about the really weird behaviors of matter under quantum conditions. So two-source interference is going to come back. We're going to hear it again and again in this course. So those are two examples of wave interference. Now, so far I've been talking about waves that actually go somewhere. But not all waves have to go somewhere. Waves can reflect, and if I have a wave that's on a bounded structure, like in a hollow pipe, for example, or in a flute, or waves on strings that are tied at opposite ends, I get what are called standing waves, waves that don't actually propagate anywhere, but nevertheless have waves happening, and the waves are going back and forth very rapidly and reflecting and interfering in a way that produces a kind of semi-fixed pattern. The pattern is oscillating in place, and it's called a standing wave. Let me give you some examples of this. So here I have a little device that will demonstrate transverse waves, and I'm going to start a transverse wave at this end, and you can see the wave propagating down, reflecting at the end, and coming back. And I want to explore in a little more detail what happens in situations like that. And I'm going to do it with this apparatus, which consists of a part from a big, powerful loudspeaker, and that's going to vibrate the end of this white string. The other end of the string is fixed. And under those conditions, only certain waves can exist on this string, because they have to be waves that have their maximum vibration here, and they have to be waves that are fixed, have no vibration going on down there because that string is tied tightly. So those are the conditions that determine, for example, what notes a musical instrument will play, a stringed instrument or even a woodwind instrument. They're also the conditions that determine, for example, what energy levels are allowed in an atom. Standing waves in quantum physics are going to be really important for understanding how atoms exist and how they have quantized energy levels. So this is a very important concept throughout physics. What I'm going to do is turn on this device, and it's going to start vibrating this string, and I'm going to hold up this black piece of cardboard so we can see the vibrations better. So here we go. You can possibly hear that vibration, but let's focus on what the string looks like as I change the frequency. You can see at some frequencies the vibration gets bigger. There's one where we got a fairly good-sized vibration, a fairly good-sized oscillation. That's a frequency which can so-called stand on this string, because it's commensurate with the length of the string and the fact that it's tied at the far end and experiences maximum amplitude at the near end. Let's look at some other frequencies. There's another one, somewhere in there. So there are these particular frequencies that correspond to standing waves that can exist on this stretched string, and other frequencies will not be able to excite the string into its vibrations. But there are many, many different frequencies, and again, they're determined by these conditions. So those are standing waves on a string, an example of standing waves that occur throughout physics. Well, let's stop there, and let's move on to one other aspect of waves that's important in everything from astrophysics to getting speeding tickets. One of the most important wave phenomena occurs when there's relative motion between the source of waves and the observer of those waves, because under those conditions there can be shifts in the frequency and wavelength of the waves, and those can be used to measure, for example, relative speeds. There are many, many applications for this phenomenon, which is called the Doppler effect. For example, if you've ever been stopped by police radar measures the Doppler effect of radar waves bounced off your car. Sports measurements of the speed of baseballs and things like that, often use Doppler shift measurements. We measure blood flow and fetal heartbeat by looking at the Doppler shift of ultrasound waves. We know that there are binary star systems with two stars going around each other because we measure the Doppler shift in the wavelength of light coming from those stars, even though we can't see the individual stars. More recently, we've detected hundreds of planets around other stars. Many of them are detected by Doppler techniques, which look at subtle variations in the velocities of the star associated with the gravitational pull of the planets. We even know that the universe is expanding because of the Doppler shift of light from distant galaxies. To explain the Doppler effect most easily, I'm going to go to a simulation that shows in green a source of waves, and when I start the simulation, waves are going to spread out from that source in all directions. If the source isn't moving, we see the waves the same in all directions. But if I let it start moving to the right, you'll see a different phenomenon. Now somebody on the right is going to see the waves closer together because the source is moving, and someone on the left is going to see them further apart. That means they're going to see a shorter wavelength and a higher frequency. If these are sound waves, they'll hear a higher pitch, for example. If you've ever stood by the highway when a truck goes by, you'll hear as the truck goes by you. You're hearing the upward shift as the truck approaches you, and then the downward shift as the truck goes away from you. And this shift occurs in different kinds of waves. It occurs in water waves, it occurs in sound waves, it occurs in ultrasound waves for medical purposes, it even occurs with light. What happens if we speed up the motion, make it go faster? And you can see the effect is now more dramatic. The foreshortening of the waves in one direction and the lengthening in the other direction is more dramatic. So we want to take an experimental look at this phenomenon also, and then we want to look a little bit at the math of it. So let's move first to a demonstration, a real demonstration of the Doppler effect. Okay, what I have here is a small loudspeaker on the end of a strong cable with which it's going to be fed by one of my signal generators I used before. So let me turn the generator on, and I'm going to whirl the speaker around in a horizontal circle. I'm not going to hear any Doppler phenomenon because I'm at the middle of the circle, but you're going to be listening with the microphone that's sitting in front of me, and that microphone will pick up the Doppler effect, and you'll hear the frequency change as the speaker comes toward you and then goes away from you. So here comes the sound, and here comes the Doppler effect. So that's the Doppler effect, the frequency shift and also wavelength shift in a signal that's carried by a wave when the source of that wave is moving relative to you. Okay, let's take a look at the mathematics of the Doppler effect. So here's a picture similar to the animation you recently saw. It shows a source that's moving to the right, and it shows an observer at A who's going to measure a shorter wavelength because every time the source emits a wave crest, the source then moves closer to that observer. Here's an observer at B who's going to measure a longer wavelength and a lower frequency as a result because the wave source is moving away from that observer. We're going to assume that the source speed is u. That's going to be the symbol for the source speed, and the wave speed is going to be v. So here's what happens. During one wave period t, the wave crests move one wavelength. We already saw that the wave speed is the wavelength divided by the wave period. So during one wave period, the wave crests move one wavelength. The source, on the other hand, moving at speed u, moves a distance, speed times time, u times the wave period, in one wave period. So an observer at A perceives a shorter distance between wave crests by that distance that the source has moved. So the observer sees a wavelength, I'm going to call lambda prime, which is the original wavelength lambda minus that distance the source has moved. The wave speed is lambda over t, as we've seen. So I can solve that for t. T is lambda over v. I can plug that in for t here. And I get lambda prime, the perceived shorter wavelength by observer A, is lambda times 1 minus the ratio of the speed of the source to the wave speed. In general, if I took observer B into account, that observer is going to see a longer wavelength, and so I'm putting a minus plus sign in here, minus when the source is approaching you, plus when it's receding from you. By the way, this formula is correct for sound waves. It's approximately correct for light waves, only with speeds much less than the speed of light. Light waves are a bit different, as we'll see when we get to electromagnetism and optics. So that's the mathematics of the Doppler shift, and let's do one example of that. We have a source speed u, a wave speed v. Here's our general formula, and here's an example. Astronomers are observing light from a galaxy at lambda equals 722 nanometers. That's a typical wavelength for light, 722 billionths of a meter. For a galaxy at rest, the same light would be at 656 nanometers. So we want to know what's the galaxy's speed. Lambda has increased, it's gotten bigger, and so the galaxy must be receding from us, so we're going to use the plus sign in this formula. We're going to solve for the quantity u over v. V in this case is the speed of light, because we're talking about light. So I solved this equation for u over v, and it becomes lambda prime minus lambda, the difference in wavelengths, divided by the original wavelength if the source weren't moving. Work that out, that's about 66 nanometers is the difference between 722 and 656 nanometers. So that's 66 nanometers over 656 nanometers, the wavelength when the source isn't moving, and that comes out to a ratio of about a tenth. And therefore we conclude that u is 1/10 the speed of light. And this is, in fact, the way astronomers measure the speeds of celestial objects, at least when they're moving toward or away from us. They can't measure sidewave speeds as easily, although they can get a handle on them. But for objects coming toward you or away from you, whether they be planets going around a distant star, whether they be pulsations of the sun, whether they be galaxies moving in the expanding universe, the Doppler shift provides us a direct way to measure velocities of different distant objects. Okay, fascinating thing, the Doppler effect. It has one more surprise for us. What happens if we really increase that speed? What happens if the source speed becomes very big? What happens if the source speed, in fact, exceeds the wave speed? We'll take a look at that next. Okay, in the Doppler simulations I showed earlier, the source was moving at a speed that was slower than the speed of the waves, slower than the sound speed if they were sound waves or whatever. What would happen if the source speed were faster than the wave speed? Then an entirely new phenomenon occurs. Let me show you. I'm going to start the animation, and I'm going to speed it up. Now the source is bouncing back and forth at a speed much, much faster than the wave speed. The waves are left behind, but what you see, let me slow it down just a little bit so it isn't going quite so fast, but still faster than the wave speed. What you see is a kind of cone of intense waves left behind from the moving source. See that cone of waves? The intense pileup of wavefronts that's occurring on that cone is called a shock wave, and it's a very strong, intense wave. With sound waves, it's called a sonic boom, and it occurs when aircraft are flying faster than sound. Not just when they break the sound barrier, by the way, but the whole time they're moving faster than sound, as this simulation suggests. Let's look at some examples of shock waves, because they occur at any time that a source moves faster than the wave speed. We see a jet aircraft flying faster than sound, and the shock wave is manifesting itself in a cloud of vapor that you can kind of see has that cone-shaped appearance. We see a boat moving through the water at faster than the wave speed. There's a V-shaped wake trailing from the boat. That's the shock wave on the water. This is a nuclear fuel rod in a nuclear reactor. It's emitting high-energy particles, so high energy that they're actually moving faster than the speed of light in the surrounding medium, which is water. And you might say, I thought nothing could move faster than light. That's true in vacuum, but it's not true in material media. And these particles are actually moving faster than light, and they're producing a kind of shock wave of light. It's called Cherenkov radiation or Cherenkov light, and that's what makes the intense glow you see there. Waves have amazing phenomena, from interference to the Doppler effect and now to shock waves. And you'll see waves occurring everywhere throughout physics.